Hello everyone, this is Muhammad Hamza from Lahore University of Management Sciences and Pakistan. This presentation is on hybrid RF plus solar energy harvesting system that is proposed in our work. And this system has applications in powering up the sensors network and nodes without having to replace their batteries again and again. So without further ado, let's begin. Our outline of this presentation is as follows. We'll start off with introducing the batteryless systems and moving into the importance of ambient sources and the scope of RF and solar energy harvesting systems recently. We'll then discuss a little bit about the state of the art, and then we will dive into the design details of our antenna and rectifier that we have proposed in this work. Finally, we'll present the results and performance comparison of the integrated system as a whole, and lastly concluding with a summary. So, as you know that there will be a huge demand in the wireless batteryless sensors in the future, and therefore there is a need to replace these batteries and power up the sensors using these ambient sources that we have. And as you know, one of the most ambient sources that is present is the RF signals themselves, which are basically omnipresent in the environment, and sensors can be powered up using these signals at any place wherever they are deployed. So one of the most important feature of these signals are that although they are present everywhere, but they are very weak in power, and their power levels are continuously fluctuating. So because of this fluctuation, the sensors that are being powered up by these signals can be turned off and turned on at times, which is not suitable for all the sensors, because they might need to be powered up. There might be a requirement to have them powered up all the time. So because of that, there's a need to rely on other power sources at the same time, so that when one goes down, the other backs it up. And for that, people have also started to rely on, for example, solar energy or some other forms of, for example, wind energy, in order to support in terms of the other as an alternative power source when the RF generation fails. So as when we discuss about the solar energy, their solar cells, they are becoming smaller and cheaper day by day, and therefore they're very easily can be used to power up these sensing networks and sensing nodes that we are discussing in this application. And since now, however, the daylight might not be available all the time, so it also is of course limited in the usage. But as we discussed right now, that one power source can back up or support the sensors when the other fails. So for example, when solar fails, RF can back up the network, the sensing network, and vice versa. So therefore, of course, it's always going to be good if we have multiple ambient sources that are powering up these sensing networks, and this will, as a result, prove to be giving us a very robust system that is working all the time. So similarly, in this work as well, we have proposed a system that combines both RF and solar and tries to eliminate the batteries from the sensing networks, and we'll discuss about it further. So when we talk about the state of the art, we have mostly the systems that are using only a single RF band to receive the ambient power, and having a single RF band might be problematic in a way again, because there might be some jammers or some deterioration or very strong interference that can lead to a very low power level in that specific band, and as a result completely failing the whole sensing network. So it's always good to have multiple bands, uh, again, because one band might not be working all the time in terms of delivering the required amount of power, or the power level might be very low um, at some times of the day in that specific band as compared to the other, which again is of course leading to fluctuations and less reliability in the system that we are presenting. So very few papers have discussed the dual band RF systems, and for example this reference 4 has proposed a system with dual band RF as well as solar integrated, but they have very high losses because of the high loss tangent that they're using, since they were using a flexible substrate. Now our work also, as I discussed earlier, combines the solar as well as the RF power sources, but we have a dual band RF signal receiver, which makes our system more reliable. And on top of that, we also have um, solar energy powered up system. So in order to make our system more robust and more reliable. And another feature is that the RF bands that we're using are from ISM bands, which are free to use, and which makes automatically this system to be used for any kind of application without being limited in terms of some licensing criteria that we will be failing to meet otherwise. Now the design of the antenna can be seen in this picture. As you can see, it's a log periodic antenna, and it's a dual band antenna, since our whole system is supposed to be a dual band, and the two bands are at 1.85 and 2.4 gigahertz with 3.84 and 5.45 dBi gains respectively. You can see that the simulated S11 results match pretty well with the measured results, and the gain requirements and the axial ratio you can see are also reasonable. And we don't have the measured gain results in this paper because of the limited resources in the university, but from the S11 and the simulated gain we can say that this antenna should be working fine in the required two bands of operation. Now we have the rectifier on that we used for the RF to DC conversion, and this rectifier is again dual band, and it's having a matching network that are defined by these transmission lines and stubs, whose dimensions are given in this table. And the substrate that we use is a very low loss, which is Duroid 5880, and we have to have this rectifier operate at a wide range of power levels. And as we know, because the rectifier is a nonlinear device, so its operation at different power levels will be different. So same goes for different frequencies as well. The operation and the efficiency will be different. So therefore we have this efficiency graph shown over here, which shows that I'm not so sure if you're able to see it, but it shows that the efficiency is higher at high power levels, and for our case, since our rectifier can at max operate at -10 dBm, so we cannot go beyond -10. So therefore we'll choose this to be our power of operation. And here we are just showing you the efficiency results at -10 dBm at 1.85 and 2.4 gigahertz, which is 52 and 42%, which is quite reasonable again. And this is just a snapshot or top view of the rectifier that we fabricated. Now the whole system integration is as shown. We have our dual band antenna that receives the RF signals from the atmosphere, and we have simultaneously a solar cell that receives solar energy and that converts it into DC. RF signals, of course, are needed to be converted to DC through a rectifier, which is again dual band, and both these DC power go to the load. We have, of course, a diode over here in order to avoid the power from the rectifier going to the solar cell. And yeah, that's pretty much it in terms of the design. And here you can see this whole system to be in together as a combination of this dual band log periodic antenna and the solar cell on top of it. Of course, the rectifier connected with the antenna in order to convert the RF signal to DC, and the solar cell connection to the load as well through these two wires. Now there's one study that we did in order to place the solar cell on top of the antenna. As you can see, it's right now placed on the non-radiating edge because the conductive trace is on the bottom layer on this side. Therefore, the solar cell was, as we studied through the measured results in the lab, was not really interfering with the performance of the antenna. And you can see from these graphs over here that with or without the placement of the solar cells, the S11 characteristics at the required bands did not really deteriorate or change. So we were happy with the results, and we knew that we can use this system together in this kind of arrangement as shown in this picture. And there was a very minimalistic change in the S11 reception, which led to us build some trust in the design. And as shown earlier, that the efficiencies for the rectifier that we were achieving were also reasonable. So we had our design of a dual band RF plus solar working in a good condition, and then the results and these two frequencies and simultaneously getting the power level from the solar cells is discussed in this slide. So as you can see that the solar cells were able to give us almost 171 microwatt power in the office environment, which is around 65 microwatt per centimeter square. So we weren't having the solar cell placed outside in the sun, but still like in a LED lit room, we were able to receive this much of power through just the solar cell. And we had our RF signal generated at -9.1 dBm, which was, as we discussed, the maximum input power level that we can give to the rectifier. was negative 10 dBm, so we just tried to be playing safe and we used a little higher, not we didn't go a lot higher than negative 10 dBm, which corresponds to 45 microwatt output power um, that goes to the rectifier. So as a result, from these two power levels that we have generated, we should be able to get around to 10 microwatt as the output. But when we did the measurements, we were able to uh, have the combined system output to be 191 instead of around 215, I would say, or 216 microwatt. Of course, it's a little less, but this power loss is due to the losses in the diode and the slightly degraded reception in antenna due to the solar cell placement. So these results were pretty reasonable and we were happy and satisfied with the performance of our system. And as you can see, the comparison with the literature, our system stands out pretty well in terms of the overall power harvested in terms of microwatt, and also in terms of having not just a single band as it's mentioned in multiple references. We had a dual band. Of course, we don't have a lot of bands as in the 4th and the 5th reference, but still we have a reasonably high amount of harvested power. So in conclusion, we presented in this work a dual band RF plus solar energy harvesting system, and we used a dual band log periodic antenna to receive the power in these two bands, and we also built a low loss dual band rectifier for this system, and we were able to harvest 192.9 microwatt of power, which was pretty reasonable as compared to the other works mentioned in the literature. Thank you very much for your time.